Unit 8, Log and Exponential Functions. This is the first set of video notes. These notes are titled in your packet, Differentiating with Logs. I'm going to be doing example 1 here. We're going to start with this function here. Let me just resize it a little bit, get a nice window on it. We'll move it up just a little bit. This is the function y is equal to the natural, y is equal to the natural log of x. And what I'm interested in is seeing if I can figure out what the derivative of this is. Right? So we're trying to figure out what is the derivative of the natural log of x. Now the way we're going to do this is by looking at a few values along the function and seeing if we can figure out a pattern as we move along the function in the derivatives. So I'm going to make a table down here. In your notes you have a table already built for you. So we're going to start with an x value, and for that x value figure out what the derivative is. That's not a very good prime. There is it. Let's try again. There we go. So let's start with an easy one. First one is 1. So if we're using 1, then we're going to have the slope of that tangent line right there, which looking at it, it's pretty clear that it's somewhere close to 1. So if you have your x value is 1, the derivative is 1 for the natural log function. If we move over and we look at what's going on at 2, so we'll draw a rough tangent right there at 2, and if we had done this a little more precisely and my grid was a little bit more accurate, you could count squares and figure out the slope of that. And the slope of that, when x is equal to 2, the slope is 1/2, or something close to 1/2. We'll just leave that one there. The third one would be looking to see what happens when we have what's the derivative at 3? So what's the slope of the tangent at 3? And actually with those two there, that's a little confusing. Let me get rid of this one. Do this again. If we're going to do it, you might as well do it sort of right. Yeah. So it's the tangent of, it's the slope of this tangent line. So at 3, if we count squares, the derivative is about 1/3. And by now you should sort of be able to guess what we think is going to happen here when we are out at 4. And again, drawing our tangent line, if I drew it, actually that one's pretty accurate. If my grid lines were a little bit more precise and I was counting squares, I would end up going up 1/4. And so then we would have, when x is 4, the derivative is 1/4. Right? So it's pretty clear. The pattern here is we're just simply doing 1/x, and it turns out the derivative of the natural log is indeed 1/x. In your notes you have a place to write that. Right, so this is one of these derivative rules that you're going to want to write down and memorize. You need to know this. The derivative of the natural log of x is equal to 1/x. Right? So now a couple examples. And in your notes, this is called example 1. So this right here is example 1a. We're going to work it the exact same way that we worked any other function that's a composite function. It's got two functions, the first function multiplied by the second function. So we're going to do the derivative of the first times the derivative of the second, derivative of the first times the second plus the derivative of the second times the first. So we're going to get the derivative is going to be equal to 3x squared, derivative of the first, times the second, plus the derivative of the second, which is 1 over x, times the first, which is x cubed. And then we're just going to simplify this. Over here, 1 over x times x cubed is going to be x squared. We have an x squared here. We have an x squared there. I'm going to factor out the x squared to sort of tidy this up. So we'll end up with an x squared here, and then inside the parentheses, after using the distributive property, we get 3 times the natural log of x plus 1. Right. Next, over here, we're in the natural log. This, again, is a composite function. What we have is one function inside another. We have x squared plus 5x inside the natural log function. So we take the derivative of the outside function, which is going to be 1 over x squared plus 5x, times the derivative of the inside function, which is 2x plus 5, and then we can just tidy that up to be 2x plus 5 all over x squared plus 5x. Third problem here. Again, a chain rule problem. This time the inside function is the natural log function. So we get the derivative of this is the derivative of the outside function, which is 5 times the natural log of x raised to the 4th times the inside function, the derivative of the inside function, which is 1 over x, and then we can tidy this up by saying 5 natural log of x raised to the 4th, all divided by x. Last one here. This one you can, we'll do this in just a sec, but if you remember your log properties, the log properties say that the log of a product is equal to the sum of the logs. Or, if you didn't understand that, you could say that this is the natural log of 174 plus the natural log of x. And now we can take the derivative of that. Derivative of the natural log of 174. Well, the natural log of 174 is a number. It's not a tidy number, but it's still a number, and the derivative of any constant is 0. Right? So the derivative of this is going to be 0 plus the derivative of the natural log of x, which is 1 over x. So then this is just equal to 1 over x. All right? So the last thing here for the example 1 notes is just reminding ourselves of the log properties, right? So if you're comfortable with the log properties, you can just write them down and you're done with this video. If you want a quick little refresher, remind ourselves that when we're saying the natural log of x times y, what we're saying is we're looking for some exponent that we use on the base e such that we get the number xy. We're looking for the exponent to put onto the base e that'll give us the number xy. Now we can think about this number x as being e to some exponent, right? So if we can find some exponent, put it on e and get our x. Same thing here. We can find some exponent for e to some exponent b is going to give us y. So instead of writing x times y, I'm going to write e to the a times e to the b, right? Because x is e to the a and y is e to the b. Now, when you multiply numbers, you're going to add their exponents. So then this is just simply going to be e to the a plus b. So now if you go back and look at this substitution piece that I did, if e to the a is equal to x, well then that means, using log notation, that the natural log of x is equal to a. And if e to the b is equal to y, then the natural log of y is equal to b. All right. Back up here, e to the y. All right. So if we take this, what we've decided up here is that e to the y is equal to e to the a plus b. E to the a plus b. Which means that, it's not e to the y, excuse me, e to the question mark, e to what we're looking for. That's this over here, right? So remember, we were looking for that. What is that? What is the natural log of x times y? Well, e to the something, question mark, is equal to e to the a plus b, which means that that something must be a plus b, which then we've just established that a plus b, a is the natural log of x, and then b is the natural log of y. Which means that this question mark, this up here that we're looking for, is really just the natural log of x plus the natural log of y. Right? So long-winded explanation to remind you of what you learned in pre-calculus. Right? So this is the natural log of x. Actually, I think you learned it in Algebra 2 and Trig, truth be told. Plus the natural log of y. When you're dividing, right? So we can think about natural log as being an exponent, right? So what is the exponent on e that's going to give us this? So I'm looking for, right here, I'm looking for an exponent. If we're looking for an exponent, if you have two numbers, you're dividing them, what do you do with the exponents? You subtract the exponents. So the natural log of a number divided by another, natural log of x divided by y, is going to be the natural log of x minus the natural log of y. Now we're going through these properties, reminding you of these properties because these properties turn out to be useful in doing derivatives involving natural logs. You're going to simplify sometimes in order to and then the last one here, sort of the intermediate step to remind yourself about why this works. If you have the natural log of x raised to some power k, well, this is really the natural log of x times x times x times x, and we've got k x's being multiplied here, right? So this is k times that we're multiplying. So then that means, if you just simply use the log rule that we had up above, that means that you're doing the natural log of x plus the natural log of x plus the natural log of x plus on and on and on. Well, how many times are you adding up the natural log of x? Well, you were adding up the natural log of x k times, which gets us to the property that the natural log of x raised to the k is equal to k times the natural log of x. And we're done with the notes, or we're done with example 1 in the notes.